love digital stuff, don't we? These days, our phones are digital, our cameras are digital, heck, even our cars are mostly digital. This here Chalk Talk you're watching, totally digital. And it's here in this super cool digital domain that we engineers get to make all kinds of magic happen. With a little help from software, of course. The problem is we live in a completely analog world. That means we have to do some serious conversion between this real analog world and the virtual digital world where we want to engineer and program. How well we can cross that analog-digital wall determines how much of that digital and software magic we will be able to perform. As we get to the cutting edge of analog to digital conversion at really, really high speeds, where the signals are screaming and the bits are flying, things can start to get pretty hairy pretty quickly. And that's why we're here today. Hi, I'm Amelia Dalton, host of Chalk Talk, and we're going to learn from an expert, David Robertson, VP at Analog Devices, about the fascinating world of high-performance converters. Before we get started, remember to click the link. There you can download a free white paper that further expands on this topic. Welcome, David. Thank you so much for joining me today.
Thanks, Amelia. Always delighted to talk about data converters in all shapes and forms, but particularly high-speed converters.
Fantastic. So we're going to talk about high-speed data converters. But before we dive in deep, let's talk about what we mean by high speed. What's driving this trend, right? Everyone wants to go faster.
Right. Well, everybody wants to be faster. Data wants to be broadband or super broadband. We've got to push more bits quicker across the pipe. But let's take a step and think a little bit about some first principles. So I've got this picture that I like to think about, something that sometimes I call Shannons Box, after Claude Shannon, who talked about the fundamental theoretical limit of how much information you could put through a pipeline is a function of two quantities. One is the bandwidth you've got in that pipe. Obviously, if you've got a wire that can handle twice as much bandwidth, we can push twice as many bits down that pipe.
Sure.
The other dimension that matters, though, is dynamic range. Again, we can use higher order modulation schemes to push more bits through a given level of bandwidth. If I push 1 bit at a time through a pipe, that's one thing. But if I can push 4 bits at a time through the same pipe, I can get 4 times as much information across.
Right.
That requires more bandwidth. So again, we think about the walls of the box being the usable bandwidth that we have available to us, and that'll typically be the sample rate of the A to D converter. And then the space between the floor and the ceiling of the box is the dynamic range.
Gotcha. Okay.
And that will help us understand the difference between the largest signal that we can capture without clipping in the converter and the smallest signal that we can detect with that full scale range.
Gotcha. Okay. So, David, what kind of applications are leading that charge?
So if we go to the next slide, we've got kind of a picture of applications plotted against those two dimensions. So on the y-axis here, I've got speed or sampling rate. Again, that's the proxy for our bandwidth. On the x-axis, I've plotted the bits of resolution, which is our first proxy for dynamic range. And if we talk about high speed, now let's talk about the upper half of this chart. So that's sampling rates at 10 megahertz or above. We've got lots of imaging type applications, digital x-ray, digital camera, things like that. But a lot of communications applications, broadband communications like base stations for wireless infrastructure, cable TV, Sonnet, that sort of thing. And then lots of instrumentation applications, things like spectrum analyzers, ultrasound machines, which are a kind of imaging system, radar systems, and other defense and aero kinds of applications that we're not allowed to talk about, or somebody in a black suit comes and takes us away.
Right. Okay, so a lot of these applications existed before, David. There were cell phones before. There were X-ray machines before. What are the changes that are taking place to push this along?
Great question. Let's kind of go to the next slide where we've got a representation of a classic signal chain. In this case, I chose a radio example.
Okay.
And in the conventional architectures, we did an awful lot of that signal processing in the analog domain. So as this would show from the antenna. First we apply some gain, then we filter out the signals that we don't want, perhaps do a frequency translation, apply some more gain, apply some more filtering,
Yeah.
do another frequency translation, and essentially get rid of all the stuff that we don't care about until we've essentially zoomed in on just the signal we care about. And at that point, we'd go into the A to D converter. So that requires a relatively modest performance, perhaps a low speed,
Yeah.
low dynamic range A to D converter, because I've done so much of the signal processing in the analog domain.
Right.
Part of the modern systems, though, what we'd like to do is replace some of that analog signal processing with digital signal processing in order to make those filters more flexible, reconfigure the system perhaps to run with different standards,
Right.
things like that. So we want to push the data converter up towards the antenna. In order to do that, I'm going to need much more bandwidth because, again, I'm not going to be able to filter some of those other signals out before I digitize.
Right.
But I'm also going to need more dynamic range. And that's because in many cases, some of those stray signals, those interferers that the filters were attacking, they may be much stronger than the signal of interest.
This is kind of sounding like a buzzword in a chalk talk hack that I've done before. Software-defined radio?
Exactly, Amelia. That's software-defined radio. They talk about software-defined instruments. And the general notion of digitize more of it, let's digitally post-process that, the fundamental nature that digital is going to be a little bit more flexible than analog. In the analog regimes, those filters that we're showing here are hardwired in through component selection.
Right.
In the digital domain, the notion that those could be reprogrammable or even push it all into a software domain ultimately if the system gets powerful enough. And I think some of the things like you've seen the very powerful FPGAs that are coming out that can now throw a lot more MIPS at a problem. All
Yeah.
of those things are basically empowering these notions of software-defined or digital processed systems. But in order to enable all of that, we've got to get the data into the digital guys, and that's a high-speed converter problem.
Okay, so I think I get it. We're talking a lot about dynamic range. What specs do we need to pay attention to make sure the converter has the right dynamic range I need?
Yeah, well, let me give you a picture now. These signal chains in this block diagram here can be a little abstract. Let's look at something in the frequency domain, and let's
Yeah.
say imagine that this is, well, let's pick something easy that we're all familiar with, the FM radio that we're listening to in our car or in our home. And the FM band is, say, 88 to 108 megahertz. And here, highlighted, I've got the one radio station that I'm trying to listen to.
Yes.
Now, in that old style, depending on how old your car is, let's say you've got your classic that's 20 years old and you've got the radio in there, and that radio looked like the previous slide, where it selected one particular station that you're trying to listen to, put that down at a 10.7 megahertz IF, and then filtered everything else away.
Right.
So that basically, as this picture showed, we zoomed into the one station that we care about, and we see that the size of that box is fairly narrow from a bandwidth perspective and also not too demanding from a floor-to-ceiling perspective, because
Right.
I have essentially filtered out all the other stronger radio stations, so now I can amplify and zoom in, and so this might be solved by, say, an 8-bit 1 megahertz A to D converter. Give me everything I need to recover that. If I now move that to a digital system where I'm trying to capture the entire band, clearly I need much more bandwidth. Instead of a 200 kilohertz bandwidth, I now need to recover a 20 megahertz bandwidth, all
Yeah.
88 to 108 megahertz. So that's pretty obvious. I need 2 orders of magnitude more bandwidth. Fine, a higher sampling rate converter. But what may not be as obvious is I need a lot more dynamic range, because now I need to recover the signal that I care about, but I also need to do that and capture the largest jamming signal, the strongest FM radio station that happens to be a radio station that I hate, but the
Right.
tower for that radio station is sitting right next to me in my backyard. So it's a very, very strong signal, maybe 50 dB stronger.
Yeah.
So instead of an 8-bit converter, I probably need a 14-bit or perhaps a 16-bit converter to digitize that, because I need to capture that strong signal so that I can filter it out in the digital domain. If I try to just zoom in my 8-bit converter on my small signal, what will happen is that strong signal will hit it, flood my converter, and that's all I'll get is clipped noise from the station that I hate.
Right.
And I think that same idea occurs in imaging, the notion that I'm trying to, say, in an X-ray, look at a tumor that's fairly faint. I've got some very strong contrast between bones and flesh.
Yeah.
I need additional dynamic range to resolve that. In many, many cases, this notion of digital post-processing is trying to recover signal that's lurking in the noise.
Right, right.
So we really need to capture, we need the extra dynamic range so that the strong signal does not clip or saturate our system. So when we talk about the kinds of measurements for dynamic range, there are many types, and I've just here listed a couple of them. Classically, in imaging systems, we talk about integral and differential nonlinearity. Again, the idea to resolve fairly small signals in the presence of large signals. We also care about chasing a fast-moving signal in many of these wideband situations. So in that case, time domain specs like acquisition time, settling time become important. As I put a stream of pixels through, I've got a very strong or bright pixel and then a very dark pixel next to it. You can imagine I need good settling time to move from a strong signal to a weak signal without having that dark pixel get distorted by the adjacent strong signal.
That makes sense, yeah.
Signal to noise ratio, again, the classic, I've got to push the noise floor down. Distortion, including total harmonic distortion, something that, again, a very strong signal can produce distortion and overload a system. Very common in audio applications, but also many high-speed communications applications care about the distortion products that are produced. So we care about signal-to-noise ratio. Again, this notion that we're going to try to pick out weak signals in the presence of strong signals.
Yeah.
Distortion, total harmonic distortion, or other ways of measuring that. There's acronyms, of course. We can't be high-tech without having acronyms.
Of course not.
Signal-to-noise ratio was too simple, so now we have SINAD, which is signal-to-noise plus distortion, or signal-to-noise and distortion, and then effective number of bits, which is a sister spec of signal-to-noise. Basically, it just translates a signal-to-noise ratio calculation into, if you had a perfect converter, how many bits would that converter be?
Right.
So all measurements of very similar things between SNR, SINAD, ENOB, those sorts of things.
So are any of these more important than the other? And these are application specific, right?
Exactly. I think that we showed the various applications on the previous page, and every application space has its own set of dynamic specifications that it cares about. Imaging applications have a different set than communications applications. This notion of spurious-free dynamic range, again, another thing related. The audio guys will talk about total harmonic distortion in terms of that tells you whether you can, in the presence of a strong signal, hear an annoying ring.
Right.
In the communication space, the sister spec for that is spurious-free dynamic range. I'll show you that.
Okay.
And the notion of noise spectral density is yet another way of thinking about noise. Perhaps it's a little easier to talk about this with a picture in front of us.
Yes, that'd be great.
Words don't do it justice. So let's talk a little bit about dynamic specs with this picture sitting in front of us.
Yes.
So here we have a strong signal with this strong tone here sitting at a relatively low frequency. We see second and third harmonic distortions. So total harmonic distortion will be from that strong signal the sum of the second, third, fourth, fifth, sixth, perhaps up through the eighth harmonic, and talk about the total harmonic distortion, the total energy in those harmonics related to the input signal. Signal-to-noise ratio will talk about the energy that we've got in that strong signal tone compared to all of the energy in the noise floor, everything else.
Gotcha.
Again, in some specs, the harmonics will be removed before we add up the energy in the noise. In other specs, SINAD, where you add both the distortion products and the noise all up. Spurious-free dynamic range, this SFDR spec, the big red arrow kind of highlights that. That is the distance between the fundamental, or the strong signal, and the highest spur, whatever that spur is coming from. It could come from a distortion product. It could come from clock leakage. It could come from 60 hertz line noise. Doesn't matter where it comes from, whatever that spur is. The notion behind that spurious free dynamic range, again, this is the elephant and the mouse again.
Yeah.
So we've got the elephant sitting there. The spurs are going to generate a whole bunch of things that look like signal, or we don't necessarily have the ability to distinguish that spur from the signal. So again, if this fundamental was the radio station we hate, and it happens that the radio station we love is sitting there right next to where that second bar is, but it's weaker than that, we're not going to be able to recover the radio station we love because the harmonic distortion from the radio station we hate is jamming that.
Gotcha.
So this notion of spurious free dynamic range determines when the elephant's in the room, how small a mouse can I see?
Right. Okay, yeah.
So the other thing that's becoming more prevalent to talk about is this NSD, or noise spectral density. And I've kind of circled this notion of the noise floor. Because again, if that elephant gets a little smaller, if I start to reduce that strong jamming signal, then all of these spurs are going to drop down in.
Right.
And what I'm going to end up with is this sort of background noise floor. So that becomes another limiting factor to the sensitivity of my system. So as I'm trying to pick up a radio station from 3 cities over, because that's the one I really love,
right, yeah,
can I pick that up, or am I going to lose it in the noise floor? And this notion of the noise spectral density tries to get at that, because particularly for broadband signals or very, very high-speed digitizing systems, this noise spectral density may even become a more useful spec than signal-to-noise ratio.
Ah, okay. So doesn't noise spectral density give you the same information as signal-to-noise ratio?
They are first cousins to one another. But
okay.
Let me show you a little bit why noise spectral density may be a better way of thinking about the noise problem.
Gotcha,
So
okay.
the signal-to-noise ratio spec talks about the total noise, which is integrated over the entire Nyquist band. Say, in this case, if this was a 75 megasample per second A to D converter, it means its Nyquist band goes from 0 to 37.5 megahertz. Let me show you this on the next slide, and maybe even clearer here with slide 8. So here we have the same picture, but what I'm showing now is even though I've got a very high-speed digitizer, 75 megahertz digitizer, so I've taken my signal-to-noise ratio and the noise is spread over the entire band from 0 to sampling rate divided by 2, 37.5 megahertz. The true signal I care about in this particular application is down here. So here's my signal, there's some harmonic there, and you can sort of see that the signal-to-noise ratio includes a whole lot of activity out here that's in my don't care band.
Right.
In my digital post-processing, what I'm going to do is I'm going to put in a filter, cut that off, and throw all of that away. So what signal-to-noise ratio am I going to have left? You can sort of see that I'm going to keep all of my signal, and I'm going to throw away most of my noise.
Yeah.
It turns out that for something with a white noise floor, and you can imagine, if I just threw away the upper half of the band, put in a filter here, cut that off, threw it away, I would throw away half the noise. That would give me a 3 dB improvement in my signal-to-noise ratio.
Gotcha.
Now, it's all digital post-processing, so the signal-to-noise ratio of the data converter is X, but as I post-processing, I'm getting X plus 3 dB. And now in this case, I can probably do that 2 more times because my essential bandwidth that I care about is only 1/8 of the actual bandwidth. So I'm going to get 9 dB of improvement in my signal-to-noise ratio. The noise spectral density then is down to what we care about. I'm going to integrate that noise spectral density over this bandwidth. So again, with this, in the world of software-defined instrument, radio, whatever, the notion of processing gain is a very, very powerful thing. I've got a wideband system. I've gone to all this work to digitize it, even when at a very high rate, even when my signal of interest is at a much lower rate. What the digital post-processing is going to do is give me this processing gain so that the actual signal-to-noise ratio in my band of interest may be several dB better than the signal-noise ratio of the overall data converter.
Right. Okay. So I'm getting a feeling that high-speed converters can be pretty powerful to enable the next generation of architectures. But what about connecting these bad boys? What about getting the bits in and out here?
Excellent question. As all of us engineers know, there is no free lunch.
Yes, indeed.
And it's never quite as easy as the marketing guy tells you it is.
No,
right?
it's
So
not.
let's talk a little bit about some of the challenges that we face. The first notion is getting the bits in and out. Part of what we look at here is the notion of different digital interface configurations.
Yeah.
And what we were all very, very comfortable with and what we grew up with is the straight TTL turning into CMOS interfaces. And for a lot of high-speed converters, a parallel CMOS interface is still a perfectly acceptable way of going. Typically, what will happen here is for a simple parallel interface, CMOS is comfortably done at 100 megahertz, and depending on how brave you are, plenty of people are out there pushing CMOS interfaces at 150 megahertz.
Yeah.
And again, pretty straightforward there. You push the data right across the bus, keep all the lanes aligned reasonably well, and you can successfully get your data across. When you want to move data faster than 100 to 150 megahertz, the next step to go is to a low voltage differential swing, an LVDS signal. Now, LVDS will be specified typically up to 800 megahertz, but again, hardy souls out there will push an LVDS interface up to as much as 1.2 gig.
Sure.
Trick with that is you need to be very careful to keep your lanes aligned there. At that point, you're pushing nanoseconds, and it doesn't take many millimeters to end up with a nanosecond of skew, and you start missing bits. So above a gigabit per second, we will tend to move to SerDes style interfaces. And again, just as we saw with the computer world and things like PCI Express to push data at very high rates between computer chips, there's an interface now for data converters, JESD 204B, that is essentially leverages the physical layer from a PCI Express type SerDes interface, and that will allow you to push bits across at up to 12.5 gigabits per second.
Nice.
So in each of these steps, you're going to spend a little bit more power. There's more sophistication. You now have software, not just behind your data converter. You have software and firmware behind your interface.
Right.
But again, it's not for the faint-hearted.
No.
But in the world now, with people are getting used to these kinds of interfaces, the FPGAs are supporting them. There's a lot of sophisticated tools, firmware, and instruments to support all of that. So this is part of the world of gigabit communication and gigahertz bandwidth and high-speed converters. So roll up your sleeves and dive in.
That's right.
The water's a little cold at first, but you'll get used to it.
You'll be fine.
That helps us with the digital interface. Another thing that I'll kind of remind everybody out there is that we showed the picture earlier where we had all of this radio processing and we're replacing mixers and low noise amplifiers and RF filters with digital filters.
Yeah.
So we need to pay a lot more respect to our clock. The clock for an A to D converter that's running at these speeds, this is not your grandmother's clock.
No.
This is not the
at
clock that you were using for your DSP processor or your FPGA. This clock now, in many cases, needs to be thought of the same way we thought of the synthesizer or the local oscillator for our mixer. Here's a little picture here to help us think about that. That if we've got some aperture error or jitter or some noise in some time domain noise in the clock line, and you think about what kind of error does that make?
Right.
Well, if the analog input is DC, then if there's timing uncertainty on the sampling instant, it doesn't matter, because if I sample a picosecond before or a picosecond after, doesn't matter because the analog input wasn't moving. But imagine that I've got a very, very fast moving analog input signal. Now you can sort of see, as that picture shows us on the right, as we have a little bit of movement in the exact instant of the sampling rate, that produces what is essentially noise or a sampling error in terms of the input that I grabbed.
Oh, okay.
And the function of that is the faster the input's moving or the higher frequency input I'm trying to grab, the more sensitive I am to the jitter. And as an illustration of that, 1 picosecond of jitter on that sampling input would limit you to 10 bits of signal-to-noise ratio for a 100 megahertz full-scale input signal.
Wow, okay.
So again, the idea that we're going to be working in the world where we've got to pay attention to the clock and we start to care about femtoseconds of jitter. You remember we talked a little bit earlier about that FM radio station. We said, well, we need 14 bits of signal-to-noise ratio to recover that. Again, an FM radio signal is going to be sitting at 100 megahertz.
Yeah.
So this is not advanced microwave or rocket science. Some fairly pedestrian signals start to have these kinds of challenges for us. So we're going to pay a lot of attention to the clocks. Fortunately, the industry's responded to that, so there are a whole bunch of clock chips now that are out there that are really specified with these kinds of performance levels, consistent with your advanced data converter systems.
Well, I think that's all I have time for today. Thank you so much for joining me, David.
Really appreciate it, Amelia. Obviously, we can talk for a couple of weeks here.
Yes, we could.
As we go in. It's always very dangerous to talk to somebody from analog devices about data converters. It's a little like asking an Eskimo a question about snow. But we will point you folks out in the audience to some resources so you can follow up for further material.
Fantastic. Before we go, don't forget to click that link. There you can download a free white paper that further expands on this topic. For Chalk Talks, I'm Amelia Dalton. For more Chalk Talks, check out the EE Journal YouTube channel or the on-demand section of eejournal.com.